We present aerial path planning for urban scene reconstruction, a continuous optimization method and benchmark. In this work, we develop an optimized camera path and view planning system for UAVs that minimizes flight time while achieving complete and dense coverage. We evaluate our continuous optimization method both in real-world field tests and on a new synthetic benchmark for image-based reconstruction of large urban scenes. The objective of our path planning is to efficiently capture complex urban scenes commonly found throughout many different cities. We formulate a reconstruction heuristic that accounts for visibility, sample density, and obliqueness of views. The reconstruction heuristic allows us to formulate path planning as a minimization problem. We first reconstruct from 100-meter altitude nadir views with high forward and side overlap. From the capture, we generate a geometric scene proxy mesh. We then compute a safe flyable airspace from the proxy that prevents the UAV from flying closer than 2.5 meters. Starting from a uniform nadir initialization, we improve the camera network one view at a time. We iteratively search for a better position and orientation within each view's local neighborhood. Through the use of GPUs, we are able to optimize the camera network of a large scene in minutes. Synthetic benchmark. Ground truth large urban scenes for path planning are hard to find. Therefore, we create 4 highly detailed urban scenes representing architectural themes from around the world. Our first dataset, NY1, is modeled after downtown Brooklyn, New York. These are primarily stone brick construction buildings that commonly display metal fire escapes and congested rooftops. Our second scene, Goth1, is modeled after the Gothic architecture found in Europe. The highlight of this dataset is the cathedral, with clock tower and difficult to capture arches and steeples. Our third scene, CA1, is modeled after the downtown storefronts found in Southern California. In contrast to other scenes, we texture these scenes with very homogeneous stucco-style texture, which proves very difficult for SFM pipelines. Our fourth scene, UK1, is modeled after the architectural styles found in the United Kingdom. All building facades have stone masonry, richly modeled along with arched entryways and pillars. Rooftops are textured with either hatched roofing or repeated wooden planks. Our final scene, called Old City, we use for testing scalability of our algorithm to handle path planning reconstruction of very large scenes with small gaps between buildings. The total size of this area is 28,896 meters squared. It is modeled after Middle Eastern architecture based on a real-world location. We generate optimized flight paths for our 4 scenes and benchmark their reconstructability with 3 SFM pipelines, MVE, ColeMap, and Pix4D. One can see, for example, in Goth1, that cameras will drop very low to see under arches, such as under the bridge. We set our airspace limit at 2.5 meters, which allows a virtual UAV to even fly between buildings to capture hard-to-reach areas. The more complex the scene, the more cameras are required, and the greater travel distance needed. Our approach is optimized to ensure the entire captured area has a maximum ground sample distance set as a variable during initialization. Here we show a visualization of reconstruction results for the NY1 scene. In our paper, we compare our method to Next Best View and Robertson author's 2010 submodular approach. We show for the Goth1 dataset we were able to capture a more complete representation of the model with less images. Complex arches and ledges that commonly occlude camera views are captured properly with our approach compared to others. For comparison, we also show the naturally covered variant of Goth1 and how it reconstructs using our method compared to the Perlin noise variant. For the CA1 dataset, we achieve greater than 10% improvement in completeness of the reconstruction, with better reconstruction of balconies, storefronts, and the umbrella shades. For the NY1 dataset, windows are poorly reconstructed in the naturally textured variant. Similarly, in UK1, the many windows in the scene are poorly reconstructed. We capture from nadir 4 scenes, this stadium along with 3 urban and residential zones with multiple buildings and challenging narrow areas. 3 more locations were chosen for field tests representing a suburban collection of houses, apartment complexes, and a modern high school. Here we display the results of our approach after capturing in the field. We are able to capture complex urban scenes with an optimized set of camera positions that take into consideration the flyable airspace of the particular area. As can be seen, nadir flight paths poorly capture building faces, while our optimized approach is able to capture these hard-to-view areas. As seen in the synthetic results, an area where improvement can be made is by increasing ground sample distance for regions that have highly homogeneous surfaces. In future work, we hope to address this. Thank you for your consideration.